On a cold January night, Betelgeuse can look like a single orange-red point sitting on Orion's shoulder, calm enough to seem almost ordinary. But if you could strip away the blur of Earth's atmosphere, separate the star's different wavelengths of light, and resolve structures far smaller than a human eye could ever see, that point would stop looking like a clean sphere and start looking like a restless, uneven, boiling world of plasma wrapped in enormous layers of gas and dust. That is the real surprise behind Betelgeuse's appearance. Not a perfect red ball waiting quietly to explode, but a changing surface, giant convective regions, an extended atmosphere, and evidence that even its strange long-term rhythm may be influenced by a hidden companion. And the most important part is that the latest confirmed story is more interesting than the viral version. Stick around because I'm about to walk you through what scientists have actually confirmed about Betelgeuse, what modern telescopes can genuinely resolve, what they still cannot, and why the star's real appearance is so much stranger than the smooth red sphere you usually see in illustrations. And if you want space discoveries broken down with the real data, not the wild guesses, subscribe because this channel focuses on what the observations actually show without the exaggeration. Let's go back to where this story actually begins. Betelgeuse is the bright reddish star marking the shoulder of Orion, one of the easiest winter constellations to recognize from much of Earth. It is a red supergiant, meaning it is a massive star that has reached a late stage of its life and expanded to an enormous size. Depending on which radius estimate and distance calibration you use, the exact numbers shift, because Betelgeuse is surprisingly difficult to measure precisely. But the basic picture is secure. This is a star hundreds of times wider than the Sun, luminous enough to be seen with the naked eye from hundreds of light years away, and evolved enough that its core is no longer living the simple hydrogen-burning life our Sun still enjoys. That sounds straightforward now. A century ago, it was not. For most of human history, stars were points. They twinkled, changed brightness, moved across the seasons, and carried colors that careful observers could notice, but their surfaces were inaccessible. Even after telescopes improved, the disks of almost every star remained too tiny to resolve. Think about holding a pinhead at a huge distance and then trying to map patterns across that pinhead. That is the problem astronomers faced. Betelgeuse helped change that. In 1920, Albert A. Michelson and Francis G. Pease used an interferometer attached to the 100-inch Hooker telescope at Mount Wilson Observatory to measure the angular diameter of Betelgeuse. Interferometry sounds intimidating, but the basic idea is simple. Instead of relying only on one clean telescope image, you combine light in a way that allows extremely fine measurements of size and structure. Betelgeuse became the first star beyond the Sun whose photospheric diameter was measured this way. That alone was historic, but it also created a problem that has never completely gone away. Once astronomers realized Betelgeuse had a measurable disk, they wanted to know what that disk actually looked like. Was it smooth? Was it symmetric? Did it have spots? Did its apparent edge move? Was the atmosphere sitting close to the visible surface, or did it extend far outward? The old mental picture was simple. A giant red star should still be basically spherical, with a photosphere that could be described by one temperature and one radius. Real stars, of course, do not care about simple mental pictures. To understand why this matters, you have to understand what happens inside a red supergiant. In the Sun, hot gas rises, cools, and sinks in a process called convection. You can see its surface granulation as a constantly shifting pattern of bright and dark cells. On Betelgeuse, convection happens on a scale so enormous that individual cells can become a significant fraction of the star itself. Imagine replacing the tiny bubbling pattern on a pot of water with only a few gigantic upwellings, each one spanning a region comparable to the orbit of a planet. That is closer to what theory predicts for a star this swollen. In simple terms, Betelgeuse is not sitting still. Its outer layers are moving. By the late 20th and early 21st centuries, interferometers began resolving asymmetries and bright regions across the star. In 2009, Xavier Haubois and colleagues reported near-infrared images from the IOTA interferometer showing two bright spots on Betelgeuse. Their reconstructed images suggested one large spot contributed roughly 8.5% of the total flux in that observing band, while another contributed several percent more. Those were not tiny sunspots. They were evidence that the photosphere itself could be dramatically uneven. Then Hubble added another layer to the story. In the 1990s, ultraviolet imaging resolved Betelgeuse's disk and showed that its outer atmosphere was not a neat shell. The star possessed extended, structured material around it. Later Hubble observations would become crucial when Betelgeuse did something that made the entire astronomy world look up. But before we get there, here's the background build that matters most. Betelgeuse changes brightness naturally. It pulsates. It has multiple overlapping timescales. It loses mass. It produces molecules and dust in its extended atmosphere. Its outer layers are so huge and dynamic that defining one exact surface can be misleading. Different wavelengths reveal different depths and different structures. That point is essential. When someone says a telescope has shown Betelgeuse's true appearance, you should immediately ask, true appearance at what wavelength? Visible light shows one version. Near-infrared light sees deeper or through some obscuring material. Mid-infrared observations can trace molecules and warm dust. Ultraviolet light highlights hot atmospheric structures. Radio observations probe still other layers. There's no single photograph that magically peels away every physical layer and gives you one final permanent portrait. Betelgeuse changes, and our view changes depending on the light we use. The pivotal turning point arrived in late 2019. Betelgeuse began fading. At first, variability was not shocking. This star is famous for changing brightness, but the decline kept going. By early 2020, it had reached the deepest visual dimming measured in modern records. To people watching Orion, the difference was obvious. Betelgeuse, normally one of the brightest stars in the constellation, had become dramatically fainter. The internet did what the internet does. Supernova rumors exploded. Maybe this was it. Maybe the giant was collapsing. Maybe humans were about to witness the nearest spectacular stellar explosion in centuries. Scientists were more cautious. They knew Betelgeuse would eventually explode as a core collapse supernova because that is the fate of a star in this general mass range. But eventually, in astronomy, is a dangerous word. The Great Dimming was not a countdown clock. A change in visible brightness could happen for many reasons, especially in a star with a turbulent surface and an atmosphere full of freshly formed material. It had exactly one chance to teach us what had happened. We needed observations across many wavelengths, before, during, and after the event. That is exactly what teams using Hubble, ground-based interferometers, photometric monitoring, and even an Earth-observing weather satellite were able to do. The first major finding is that the Great Dimming was not simply the star switching off. Andrea Dupree of the Center for Astrophysics, Harvard and Smithsonian and colleagues assembled ultraviolet spectra and other data to reconstruct a violent sequence in Betelgeuse's atmosphere. Their work, published in 2022, argued that the star experienced a substantial surface mass ejection. The term is similar to the solar idea of an eruption throwing material outward, except the scale involved at Betelgeuse is vastly larger. The proposed sequence is remarkable. A disturbance traveled through the star's atmosphere, material was ejected, part of the photosphere cooled, and expelled gas moved far enough from the hot star to allow dust to form. That dust then obscured part of Betelgeuse from our point of view, contributing to the dramatic visible fading. In other words, the star did not have to become proportionally less luminous everywhere. Part of what happened was between us and the light. This is where a beautiful result from a completely unexpected instrument enters the story. Daisuke Taniguchi and colleagues used archived observations from the Japanese Himawari 8 weather satellite. Himawari 8 was designed to monitor Earth, not red supergiants, but Betelgeuse occasionally appeared in the background of its images. The team extracted years of multi-wavelength measurements extending from visible light into the infrared, and their 2022 Nature Astronomy paper supported a combined picture involving both photospheric cooling and dust formation. I love this detail because it captures how science actually works. A spacecraft built to watch clouds and storms on Earth accidentally helped diagnose a stellar event hundreds of light years away. If that kind of cross-mission detective work is the reason you watch this channel, drop a like. It tells the algorithm there is an audience for the careful version of the story, not just the loud version. But that was just the beginning. There is a second discovery, and this is where Betelgeuse's actual appearance becomes even more alien. In 2024, a team led by Jay Dreven reported interferometric imaging of Betelgeuse using Matisse on the European Southern Observatory's Very Large Telescope Interferometer. They studied the star before, during, and after the Great Dimming, focusing on a mid-infrared region containing signatures from silicon monoxide, or SiO, a molecule common in the extended atmospheres of cool, evolved stars. Matisse does not give you a normal snapshot in the way a phone camera does. It combines light from multiple telescopes separated across the observatory, effectively creating the resolving power of a much larger instrument. The team reconstructed images to map how emitting and absorbing material was distributed. What they saw was not a stable, symmetric shell. The SiO distribution was strongly inhomogeneous and changed between observing epochs. That is scientific language for something visually profound. Betelgeuse's atmosphere was patchy, uneven, and evolving across time. Picture a globe whose apparent edge is wrapped in translucent layers. Now imagine those layers thickening in one region, thinning in another, cooling, heating, moving, and chemically changing. The surface becomes less like the clean boundary of a solid object and more like the glowing top of a deep, moving fog. That is closer to Betelgeuse, and this is why no single dramatic image should be treated as its permanent face. The photosphere is dynamic. The molecular environment is dynamic. The circumstellar dust is dynamic. Even the radius depends partly on what wavelength you choose to measure. The deeper lesson is that the old textbook sphere was never exactly wrong. It was incomplete. At large scale, Betelgeuse is still a gravitationally bound star and approximately spherical. But once you resolve the details, symmetry gives way to weather-like complexity on a scale that is difficult to comprehend. Now we arrive at the third finding, and this one tends to unsettle people the most because it changes the story from one giant star to a system. For decades, astronomers had noticed that Betelgeuse showed a long secondary period of roughly 6 years, in addition to shorter variability. The cause was debated. Pulsation? Giant convective behavior? Something in the atmosphere? Or a companion? In 2024, independent analyses strengthened the companion idea. Then, in July 2025, a team led by Steve Howell of NASA's Ames Research Center reported probable direct imaging of a companion using the Alupaki speckle instrument on the Gemini North Telescope in Hawaii. The observations compared epochs when the predicted companion should have been difficult to see, with a later epoch near its expected maximum separation. The result was a faint source around 52 milliarcseconds from Betelgeuse, about 6 magnitudes fainter in blue light, in a position consistent with orbital predictions. Let that scale sink in. 52 milliarcseconds is an absurdly tiny angle. A milliarcsecond is 1,000th of 1 arcsecond, and 1 arcsecond is already only 1/3600th of a degree. This is why resolving the Betelgeuse system requires techniques that go far beyond ordinary imaging. Then, in January 2026, Hubble observations combined with ground-based data added another clue. Researchers led by Andrea Dupree reported evidence of a wake in Betelgeuse's outer atmosphere associated with the companion's passage. Think of a small boat moving through water and leaving a disturbed trail behind it. Here, the water is not water at all. It is the extended gaseous atmosphere of a red supergiant. This companion has been informally nicknamed Sawarha in recent work, following an Arabic-derived name connected with Betelgeuse's historical naming tradition. The important scientific point is not the nickname. It is that a relatively faint companion may be orbiting inside or through the giant star's extended atmospheric environment, affecting measurable spectral behavior. And then there is the detail that makes the system feel almost impossible. Betelgeuse is so physically enormous that the companion's orbit is not like Earth circling far outside the Sun's visible body. The geometry places the companion astonishingly close to the supergiant, in an environment filled with material lost from Betelgeuse. Researchers are still working out the exact nature, mass, and evolutionary history of the smaller star, but the broad picture is now much more compelling than it was only a few years ago. So when a viral thumbnail shows a clean red sphere and labels it Betelgeuse's final true appearance, remember what the observations are telling us. The real object is messier, much messier. And if you have made it this far, drop a comment with the part that surprises you more: the giant moving surface, the dust cloud behind the great dimming, or the hidden companion. I'm genuinely curious which one changes your mental picture of Betelgeuse the most. At this point, we need to address James Webb directly. The James Webb Space Telescope is extraordinarily powerful, especially in infrared astronomy, but there is no official NASA, ESA, or Space Telescope Science Institute announcement matching the claim that Webb just revealed a brand new, definitive, true appearance of Betelgeuse 1 minute ago. The major recent confirmed Betelgeuse results discussed here come from instruments including Hubble, Gemini North, the Very Large Telescope Interferometer, and long-term multi-wavelength monitoring. That distinction matters. Webb could contribute enormously to the study of evolved stars and circumstellar material, and its infrared capabilities are ideal for many questions involving dust, molecules, and stellar environments. But credibility means not assigning a discovery to Webb simply because its name makes a stronger headline. The real data are enough. Now picture for a moment what it would be like to approach Betelgeuse, not in a spacecraft that could survive the trip, because nothing we can build could casually hover near a red supergiant, but as an impossible observer, protected from the radiation and heat. At first, there would be no familiar solid surface below you. The star would fill your sky with a dull orange-red brilliance, but the color would not be uniform. Huge regions would appear brighter and hotter, others cooler and darker. The visible boundary would soften into extended layers. Gas would rise and fall across distances that make Earth look microscopic. Material would stream outward. Molecules would form in cooler regions. Farther away, dust could condense from gas that had once been part of the star itself. You would be watching a star lose its body into space. Move outward and the scene becomes even stranger. Betelgeuse has created an extended circumstellar environment through mass loss. The gas around it does not sit in a perfect bubble. It interacts with the star's motion through the local interstellar medium. Infrared observations have revealed large-scale structures including arcs and a bow shock-like region ahead of the star's direction of travel. Now compress years into seconds. The giant surface shifts. Pulsations move through the outer layers. A convective region swells. Material rises. A disturbance propagates. Gas is thrown outward. A patch cools. Dust appears. The visible star fades from your distant point of view, even though the underlying event is not a supernova. Then the atmosphere reorganizes, the brightness returns, and somewhere close to this enormous turbulent body, a much fainter companion continues its orbit, potentially cutting through the extended atmosphere and leaving a detectable disturbance behind it. That is not the face of a quiet star. It is an ecosystem of stellar physics. To understand why this matters beyond one famous point in Orion, zoom out to the class of stars Betelgeuse belongs to. Red supergiants are a late evolutionary phase for massive stars. They are laboratories for one of the biggest unresolved problems in stellar evolution: exactly how massive stars lose material before they explode. Mass loss changes everything. It affects the final mass of the star, it affects the structure of the material surrounding the star, it influences what astronomers will later see when the supernova shock crashes into that material. It helps determine what kind of compact remnant may be left behind, and it enriches the galaxy with elements that can become part of future stars, planets, and eventually chemistry like the chemistry inside us. Betelgeuse is especially useful because it is close enough, by astronomical standards, for us to resolve details that would blur together in more distant red supergiants. It is like having one nearby giant laboratory where each new instrument can test a different layer of the same problem. That is exactly what interferometry was able to do. That is exactly what Hubble's ultraviolet spectroscopy was able to do. That is exactly what long-term monitoring was able to do. And it is why future observations matter so much. A single image is a snapshot. Betelgeuse demands a movie. Researchers need repeated measurements across different wavelengths to separate pulsation from convection, dust formation from temperature change, orbital effects from random atmospheric structure, and ordinary red supergiant behavior from genuinely unusual events. This also brings us to the supernova question, because I know where your mind goes whenever Betelgeuse appears in a headline. Yes, Betelgeuse will explode one day. No, the Great Dimming did not prove it was about to explode. No, the discovery of a companion does not give us a countdown. And no, scientists cannot currently tell you the exact year, century, or near-future human timescale of its final collapse with the confidence implied by viral headlines. Stellar evolution models can tell us that Betelgeuse is in an advanced state compared with the Sun. They can constrain its likely evolutionary path. But translating observations of a red supergiant into a precise explosion date is another problem entirely. Honestly, this is where the uncertainty makes the story better, not worse. If we knew the exact final moment, Betelgeuse would become a timer. Instead, it is a living laboratory whose surface and atmosphere are changing while we watch, and every new dataset forces astronomers to separate several overlapping processes. The companion makes that harder and more interesting. The Great Dimming makes that harder and more interesting. The huge convection cells make that harder and more interesting. And the fact that every wavelength shows a slightly different version of the star makes the phrase true appearance almost philosophical. What does a star really look like? To your eye, Betelgeuse is a red-orange point. To an optical interferometer, it is a resolved disk with asymmetries. To an infrared instrument, it can reveal different molecular and dusty structures. To Hubble, in ultraviolet light, its extended atmosphere becomes a major part of the story. To spectroscopy, it is not an image at all, but a forest of chemical fingerprints and Doppler shifts telling us how gas is moving. None of those views is fake. Each one is true at a different physical layer. That idea extends far beyond Betelgeuse. Astronomy is full of objects whose appearance depends on the wavelength you choose. Dust clouds that look black in visible light can glow in infrared. A galaxy that looks calm to your eye can reveal violent star formation in ultraviolet. Hot plasma, invisible in ordinary light, can blaze in X-rays. Modern astronomy is not simply about building sharper cameras. It is about learning to see forms of light your eyes were never designed to detect. And Betelgeuse is one of the best demonstrations of that principle because we already think we know what it looks like. We have seen the orange point. We have seen the illustrations. We have seen the smooth, glowing sphere in thumbnails. Then the data ruin the simplicity. So, what does all of this actually add up to? First, Betelgeuse's visible disk is not a smooth, fixed surface. Interferometric observations have revealed large-scale asymmetries and bright regions consistent with gigantic convective activity. Second, the star's atmosphere extends far beyond a simple photospheric boundary and contains molecules, gas, and dust whose distribution changes with time. The Great Dimming showed how dramatically those outer layers can alter what we see. Third, the 2019 to 2020 fading was not convincing evidence of an imminent supernova. Multi-wavelength observations support a combination of surface cooling, mass ejection, and dust formation as key parts of the event. Fourth, evidence for a close companion has moved from a long-running hypothesis to probable direct imaging and atmospheric wake signatures, giving astronomers a new factor to include when interpreting Betelgeuse's rhythms. And finally, there is no verified official announcement that James Webb suddenly delivered one definitive portrait that replaces all previous views. The scientifically responsible version is richer. Multiple observatories, over decades, have assembled a changing three-dimensional picture of a star whose appearance depends on time, wavelength, and physical layer. That is the transformation. The orange point on Orion's shoulder has become a place. Not a place with ground you could stand on, but a physical environment with moving plasma, enormous convective structures, ejected material, molecules, dust, shocks, pulsations, and perhaps a small companion carving its path through the outskirts of a giant. It is worth pausing on the scale. The light entering your eyes from Betelgeuse tonight began its journey centuries ago. The star you see is already historical. Whatever its surface is doing right now, in the star's own local time, we will not know until that information crosses the enormous distance between us. That delay creates one final paradox. Betelgeuse is one of the most closely watched massive stars in the sky, yet we can never see it now. We see an ancient message. Every photon is a piece of history. Every interferometric measurement, every spectrum, every reconstructed image is an attempt to read that message more precisely. And that brings us back to the image we started with, one quiet orange-red point sitting on Orion's shoulder. From your backyard, it still looks simple, but simplicity is what distance does. Resolve the point, separate the wavelengths, follow the star through time, and the clean sphere dissolves into something far more extraordinary. A restless red supergiant changing on scales large enough to swallow the inner solar system, shedding its own material into space, carrying enormous structures across its surface, and interacting with an environment we are only beginning to map. No exaggeration is needed. The real Betelgeuse is already strange enough. And one day, whether that day is far beyond our lifetimes or unexpectedly closer on an astronomical scale, the physical story will end in core collapse. When that happens, the quiet point in Orion will become something no human civilization with modern instruments has ever observed at such proximity. A nearby massive star supernova studied across the electromagnetic spectrum with an entire planet's worth of telescopes ready to respond. Until then, Betelgeuse is giving us something arguably more valuable than a countdown. It is giving us time. Time to watch a massive star breathe. Time to see how it loses material. Time to test how giant convection really behaves. Time to understand how a companion may influence an evolved supergiant. Time to improve the models we will eventually use to interpret the explosion. And time to learn that the true appearance of the universe is rarely the version our eyes show us first. If you want to follow that story as more data come in, subscribe and turn on notifications, because Betelgeuse is still being monitored and future observations can change the details. Drop a comment telling me which view of Betelgeuse you would most want to see for yourself. The boiling photosphere, the dusty outer atmosphere, or the hidden companion moving through the system. Share this video with someone who has heard the supernova rumors, but never saw the science behind them. Thanks for watching, and I will see you in the next.